Hi everybody, I'm Clement and I'm with Thomas today to speak about some Windows internals. So today we're going to talk about our research about ALPC, which is a way to communicate in on a Windows computer, and RPC, remote procedure call. So let's go right away. First of all, where does the talk come from? It comes from, we were curious about the UAC, or user account control. The UAC is a little window that pop out when you want to try to launch a process as admin. So, for example, when you right-click on PowerShell and say Start PowerShell as admin, you have a little window that say, do you want to really launch PowerShell as admin? And you say yes or no. And this is user account control, or UAC. And we wanted to launch the UAC from some script, some Python script, and the only API we found was shell execute. And it's like a really complex API and really complex under the hood that do a lot of things. And we wanted to be like bare metal. And we wanted to trigger it manually. And what we knew is that the UAC might be triggerable using remote procedure call, and that the ALPC system on Windows may allow us to perform RPC, so remote procedure call. So together, let's explore the world of RPC over ALPC on a Windows computer. There are a few existing research about this subject. The first one from Thomas Garnier in 2008, and two in 2014 from, of course, Alex Ionescu and Ben Nagy. And we used also a tool named RPC View, developed by a few guys, which allow you to see all the RPC server running on a computer. And it's a really useful tool. We used it a lot during the last few months, and we will show you some screenshots during the presentation. So first of all, what are the ALPC? ALPC stands for Advanced Local Procedure Call. It's the new generation on Windows computer of the LPC, Local Procedure Call. It's kind of a client and server relationship. So you have a server listening on an ALPC port. An ALPC port is just a Windows name object of type ALPC port. And you have clients able to connect to that port. And after connecting to the ALPC server, exchange message between the client and the server. And the ALPC exchange are composed of two ports. A port message, which is an header and the raw data of the message, and the ALPC message attribute, which are a set of attribute header and a set of attributes that will be used for advanced feature that we will see later in the presentation. So what is a port message actually? A port message is a simple struct that have few interesting fields. Like the first one is the data length, which is the size of the data after the header, so without the header. After that, we have the total length, which is the size of the header plus the size of the data. And we have the type of the message. Each message has a given type, so the type we will see today are the connection request type, when a client tries to connect to a server, and the request standard type, which is a standard RPC message. After that, we have also a client ID that allows the server to identify the client using the unique process ID and the unique thread ID. And last of all, we have the message ID, and the message ID allows the kernel and the server to identify a message. So when you send a message back with the same message ID, the kernel knows that it's a reply to a given message. So the client sends a message, the server gets a message with a message ID, and when you send back the same message with the same message ID, the kernel knows that it's a reply. Given that, all we need now are the API used to do ALPC communication. So a server is able to create a port using NT-ALPC create port, accept a connection, and we have the main API, which is NT-ALPC send, wait, receive port, which allow you to either send a message, receive a message, or do both. Send a message, wait, receive a message. And it can be done both synchronously or asynchronously. And the last one for the server is a TP callback send ALPC message and completion, which is kind of a really obscure API used by RPC RT4.dll, which is the RPC runtime. And we just put it because we found the reverse engineering and for the documentation purpose, sorry. And the client, it's even simpler. It's able to connect to a port using NT-ALPC connect port, disconnect from a port, and send message to the server using the same API, so NT-ALPC send, wait, receive port. Using that, we were able to do a full Python implementation of an LPC server and client. So every piece of code on this presentation will use a project named Python for Windows, which is a personal project I've been working on for the last 2 years. And it's the code have been pushed like 10 minutes before. So it's already online. So the first part is the ALPC server itself. So an ALPC server just create a port of port name and wait for a message. The first message we will get is a message of type LPC connection request, because the first message is a message sent by the client when he tries to connect. So all we do is accept the connection, and after that we wait for a real message, and the real message will be of type LPC request. And all we do is change the data of the message to request done, and this port being replaced by the message data sent by the client. And we send back the same message. The client is even simpler. We have an LPC client which connects to a given name, to a given port, and sends the message hello world and wait for a response. And the response, of course, contains the following data, so request hello world done. So we have the proof here that the message was indeed sent to the server handled the connection, the message, and sent us back this message. Based on this Python implementation of ALPC communication, we are able now to explore the RPC system on the Windows computer. So RPC stands for Remote Procedure Call, and RPC describe, in fact, the ability to perform a call of a function which is not in your own address space. So we call a function that is in the address space of another processes. A process, for example, that have better privilege than yours or stuff like that. And for that, we have few issues, like how do we communicate with the server, so with the other function processes, and how do you serialize and deserialize your parameters. On Windows, the server has one or many endpoints. An endpoint is a way to connect to the server, and depending on the protocol you're using for the communication. For example, if you have an IP TCP connection, your endpoints will be an IP on a port. If you have a name pipe connection, your endpoint will be a name pipe. And if you have an LC-ALPC type of connection, so ALPC connection for RPC remote procedure call, your endpoint will be, of course, an LPC port. So a few images being better than a thousand words. Here are a few screenshots about RPC view. So the first part of the screenshot show you a process named svcos.exe, which is running the app info service. After that, you can see that the endpoint of this server is of type NC-LRPC. So we have an LPC port for as an endpoint, which is LRPC.4.b. And this server serves one interfaces named 20E1 of version 1.0, which is located in appinfo.dll. So the code for this interface and the methods of this interface are in appinfo.dll. And this interface serves 7 methods, which are described here. And for example, the method number 0 is array launch admin process, which is the API we will use later to call the UAC. So now, how do we perform actually an RPC call? There are 3 steps. The first one is directly linked to the protocol you will be used. It's a connection step. So for ALPC connection, we just use the API we saw before. So we will use NT-LPC connect port to connect to the port. The server will accept the connection, and we are connected. After that, we need to bind to a given interface. The binding phase is like a negotiation. You will send the information you want and how you want to bind yourself to a given interface. So you need to give the unique ID of the interface, the syntax version, the interface version and the syntax version. The syntax version just describes the method of serialization that will be used, and we will see it afterward. And an interface ID which will be used afterward to describe the interface we just bind to. You send that to the server handles the request and send you back the information. And after that, we are able to perform RPC call. So for RPC call, you need the interface ID you just bind to, of course. You need the number of the interface you want to call. So the first one, the second one, whatever. And you need, of course, as it is a function call at a given time, you need the parameters you want to use for the call. And the parameters are serialized using NDR. We will go back to NDR a few times after that. So under the hood, what is a RPC bind request? It's a destructure. So there is a lot of unknown field, because it's the result of our work of reverse engineering. So we don't know if it's padding, if it's stuff that are not used, or we don't know what is it. So the first field is a request type, which will be RPC bind request. The target describes the interface we want to bind to, so using the interface unique ID and its version. And the flag describe like if you want to bind given the NDR32 serialization method, NDR64 serialization method, or whatever. You can bind to many syntax versions at the same time, and for each syntax we want to bind, you have an interface number to fill out here. So if you want to bind to both NDR32 and 64, you need to give two different interface numbers that will be the interface ID afterward. To build a minimal request is quite simple indeed. You have to craft an ALPC RPC bind request of type of core RPC requesting bind. The target will be the unique ID of your interface and the version of your interface. The flag, for example, will be to bind using NDR32, and the request ID is put in interface ID for the NDR32, and you put whatever you want to use as interface ID. And the response is also an RPC bind request, of course, of type RPC bind type OK, and the fact is that some fields that are sent back to you may have changed because it's a negotiation method. So like if you ask for NDR32 and NDR64 and the server don't know how to use 64, it will just send back the same packet but without the 64 information. So it will wipe out the flag NDR syntax 64 and wipe out the interface number 64 from the packet. So an RPC call is an even bigger structure with even bigger unknown field, but we have enough stuff to like send RPC call and do exploitation, so it's okay for us. The first field is also a request type. We have the flag. We have no information about what they done, so 0 is okay, sorry. The request ID is just an identifier for the request that will be sent back to the response. It's used for example, asynchronous client that make multiple call and get multiple response afterward. The interface number is of course the interface number we bind to before, and the method offset is offset the method you want to call. And after this structure, you have the parameters serialized that are appended to this structure. So to build a minimal RPC call, it's even simpler. You have to craft an ALPC RPC call, set the type to RPC request type call, set the request ID to whatever you want, set the interface ID to the interface method number that was the result of the binding before, and the method offset to method offset, which is the offset of the method we want to call. And after this buffer, all you have to do is append the params, and parameters are the marshalling, the result of the marshalling the method. Speaking of marshalling, so I used NDR a few times without presenting it, so it's time. NDR stands for Network Data Representation, which is a serialization method which is documented online. And the description is just that the role of NDR is to provide the mapping of ideal data type onto a text stream. It's like the basic definition of a serialization protocol and method. And we have windows that over that offer few transfer syntax, so few various type of this NDR transfer serialization method. The first one is like called NDR. We call it NDR32 because pointers are encoded on 4 bytes. And there is NDR64, which is the actual name, where pointers are encoded on 8 bytes. And we found during reversing in the runtime of RPC, the RPC runtime, this unique ID describing another transfer syntax. We have no information about it. There is nothing nowhere. We have not even a name. So if you have any information about this one, please tell us. We will be glad to have some information. And as part of our project and our research, we implemented part of NDR32 serialization and deserialization in full Python, in Python for Windows. So given all those information, we are able to abstract everything out because it's quite complex. And we were able to create an RPC client, in full Python. So here is a little example. We have an RPC client that connects to the LPC port RPC control, LOLPC. And we bind to a given interface. The default version we use is 1.0. After that, what we do is that we get the bind interface ID, and we use it to call the method number 1 of this interface. The method number 1 is just a server-side add, so it takes 2 int and adds the 2 int and sends you back the response. So of course we pack our 2 int right here in the call. So the parameters we send is 41, 41, 41, and 111. And we make the call. You can see that the server gets the request of adding 2 numbers, sending the response. The response is also NDR serialized. So we are able to unserialize a long from the response, and the result is 42, 42, 42. So the addition was done server side. To show you that we are also able to call multiple methods from the same interface, we take the same interface ID, so the interface 41, 41, 41, and call the method number 0. The method number 0 is like a remote printf, so it just print a string. We send it hello from Python, and you can see that the interface 1 print hello from Python. That's it. And last of all, to show you that we are able with the same client to bind to multiple interfaces, we bind to the interface 99999, given us another interface ID, and we call the method 0, which is also another remote side printf, and we send it hello again from interface 2, and you can see that the interface 2 indeed call hello again from interface 2.
So now we are able to connect and bind and perform RPC call. So, but we don't know where the endpoint of an interface is located. So how do we get the endpoint for a given interface? For that, the endpoint mapper RPC service exists. It allows to query for endpoint names and to register endpoint names. It's available at a fixed ALPC port name, pmapper, which is located in RPC control object directory. The method that interests us is the method number 7 called eptmapout, which allows to query for an interface endpoint. It takes two parameters, so a security identifier and a protocol tower. The protocol tower is a described binary format, and it's described online if you want to check out this link. And it's allowed to describe the interface information, so the interface version, the interface identifier, syntax version, and also the interface endpoint, what we are interested in. Let's see an example. So we implemented the RPC call in Python. So here we implemented in find ALPC endpoints. If we want to find the interface number 880FD, and we ask only for two response, we get back two towers. So this is our protocol towers that are referring to ALPC port, because the protocol is NCR ALPC. And they give us back two endpoint names, which are LRPC-B0 and OLI-8C. And we can connect to this ALPC port, in order to bind to the interface 880FD. We also implemented a method called find ALPC endpoint and connect, which allow to do the job for us, so finding the endpoint names and connecting to it. And so this returns a Python object called RPC client, which is already connected to the good port in order to perform the bind afterward. So let's go back at our first field of interest, the UAC. So Clement already said that the UAC is implemented in ARI launch admin process in APP-info, the method number 0 of the interface identifier 21E. The method ARI launch admin process takes the following parameter: an application path, which in our case is MS Paint. This is the application that we want to launch as admin. The command line, so we can control the command line, and the process, create process flags and structure. So this RPC call will result in the UAC method, UAC window popping out, with the program Paint and the command line we control. So while developing and reversing how to understand how the UAC work, we found the auto-approved list of trusted binary that allow to bypass the UAC for a certain list of binary. In that whitelist, there is a special case for mmc.exe, where the command line is actually parsed to analyze which MSC file will be loaded by mmc.exe. And there is also a second whitelist with the MSC file that are whitelisted and they will bypass the UAC. And in the command line parser, to analyze the command line of mmc.exe, the comma is treated as a valid command line separator. So as we can fully control the command line, we can craft the following command line: xxx, wf.msc, which is the window firewall MSC file, which is whitelisted and will bypass the UAC, space my bad MSC. And APP-info RPC service will think that the wf.msc is the target, so it's whitelisted and will not pop the UAC, but mmc.exe will load the malicious my bad MSC. But we can control the my bad MSC, and with the MSC file we were able to have admin code execution using an ActiveX control flash object and calling an external method called execute shell command. The full steps to perform this UAC bypass are described in the following talk. Go check out if you are interested. So now we found a UAC bypass, but we were interested to go further and try to find local privilege escalation. For that, we took two approaches. The first one was reversing and understanding the ALPC advanced feature, and the second one was fuzzing the exposed method of RPC. So the ALPC message attributes are a sample structure here with only two fields, which said which attributes are allocated. So here the data view attribute and the under attribute are located just below the ALPC message attribute structure. And the valid attribute refer to which attributes are valid and will be used for the ALPC exchange. So here the data view attribute. These attributes allow to perform some advanced feature. So let's see what can you do with that. So you can use the security message attribute to change the quality of service option, the view attribute to send the data in a shared memory instead of having after the port message. This view attribute will be interested in after. And you have also a context attribute which allow to expose some message ID, and even an handle attribute which allow to share handle between the client and the server. So through ALPC you can share object handle. That's interesting. And the last one are new to Windows 10 and we didn't look at them. So let's see an example of how to share a file handle with the server. So we just open the file. So here it's rpc-rt4.dll, which is the RPC runtime, but you can do it with any file. You craft the ALPC message. You set the ALPC message handle attribute as valid in order to be used for the exchange. You fill the handle attribute with the handle from the file and some flags. And simply you send the ALPC message. And the server is receiving the ALPC message. And can extract, it sees that the handle attribute is valid and can extract the object types, which is one, meaning that it's a file object transferred through ALPC. And it can extract also the file handle and get an handle directly of the file sent by the client with the same privilege because we use the flag duplicate CMX. And in the same time as reversing, we were doing some fuzzing. So why do some fuzzing? Because there are over 150 RPC interfaces in Windows just only from Microsoft. A lot of them are privileged and accessible from low integrity, so like a sandboxed process. And so we wanted to try to find bugs in these RPC methods. So at first we built a simple RPC man-in-the-middle fuzzer performing mutation on the serialized stream. So just to alter, to modify the parameters that are sent during RPC call. And that was built in the top of a RPC debugger, so debugging only one process at a time, not doing in kernel but in userland. So we were not targeting all the exposed method of RPC. We are only targeting the ones that are used by the program when launched. So to counter this problem, we developed another fuzzer called RPC Forge, which allows to forge call for any interface method. The main issue with forging call is that the RPC server runtime, the RPC runtime in the server, will not accept the RPC call if the parameters are not correct. If the parameters are not correct. So the serialized stream sent by the client must match the interface method parameter and types. If the type doesn't match during the deserialization, the RPC runtime will block the call and you will not be able to access the server method. So here are the steps how RPC Forge works. So first it's connect to an interface through endpoint mapper or fixed ALPC endpoint name. Then it generates the call argument with the correct types and structure in order to not to be blocked. And the generation is based on Sule generator, which is an open source fuzzer. And perform the call with the Marshall parameter and extract any context handle from the return stream, because the context handle is an endier type that can be required for some calls. A context handle is actually a client identifier, so an identifier sent by the client to the server, which refer to any custom server object. So you can, the server can handle a custom object and the client send them using identifier that are returned by the server. So basically, it's like a PHP session. You send a cookie, and the server can store anything that you want in your session, not in the cookie, but in your session. So this is server-side object. So let's see an example of how the NDR stream is generated. So the interface Python code is generated using RPC view, the tool Clement showed you before. It's a customized version. It's not generating Python code, but we build it to do that. So if we want to fuzz the IP transition protocol apply conflict change X, which takes 3 parameters, a byte, then a long, then a string. The string size is referred by the parameter 2, and so this long is the size of the string, and it's bound between this value. So we simply have a method called named forge call, which forge directly the serialized call for the method. You can see the size twice and the string. We connect to the interface and call the method. You can see that the result value is 0. That means that the call has been accepted, and the RPC runtime has not blocked our call. So we are calling the remote method. The RPC Forge will be released on GitHub after the conference. So with RPC Forge, we were able to find multiple bugs, approximately 10, and most of them are null difference of or out-of-band access due to invalid check. So either a null pointer or integer that are not checked between the range, so doing out-of-band access. We also found a type confusion bug due to context handle. So if the server-side objects, custom server-side objects are of different kind, and you send an identifier of different object to the server, it will not be expecting that type of object and can lead to type confusion. So we did find a type confusion due to context handle problem. So Microsoft has a way to fix it using type strict context handle. And we also found some logical bug because the client privilege were not checked. All of these bugs can lead to service DOS, so crash in the service. A system DOS if the with a blue screen critical process died if the service was running in a critical process, or even privilege escalation. Let's see a funny example of a Microsoft anti-malware service. So it is accessible from low integrity at the fixed ALPC endpoint name, EMP service and some character after. So we can connect and bind to the interface. A funny method is called server MP RPC force reboot, which allow to reboot the computer. So without having the privilege to reboot the computer, any low integrity process can call this method to reboot the computer. Another funny thing is that the RPC runtime RPC-RT4.dll leak heap server memory in the receive buffer during the RPC exchange. Sorry. And if we call a dummy method here MP query engine version, after the return parameter, the return value, you can see some string that shouldn't be there, and that's referring to Microsoft Edge and some path leaked by the Microsoft anti-malware service. We did find some more interesting bug that allow us to perform a local privilege escalation. So this was patched in October Patch Tuesday. So let's start with the beginning. We were thinking and we were curious about the shared memory. What is handled? Is it available for any RPC server? Which data is in there? And how it is protected during the core, RPC core. So you already know that shared memory exists as ALPC view attribute, as I said before. So to understand how it works and how to craft a message with a view, we reverse the NT API, NT ALPC create portion section and create section view to understand to build the view in the context of the client, and when the message is sent using ALPC send wait receive port, the server will the view will be mapped in the server context too. And we saw, after reversing all of it, that Alex Ionescu already documented all this thing and developed a little C implementation of with the view. So we did find an interesting bug, logical error due to the flag 40,000. We will call it secure view, but it's not actually the Microsoft name for it. We can encounter this flag in two functions in kernel, anti-ALPC create power section and capture view attribute internal. This flag allows to secure the view, so set it as read-only. Set the view in the client, so the shared memory in the client as read-only when the ALPC exchange occurs. The RPC exchange occurs. So, and RPC runtime in the server side will actually can handle the call request with the view. It can handle that because there are some attributes it cannot handle. And with the view attribute, by default, it will copy the shared memory contents. So the data of the shared memory to a local buffer before doing the serialization and passing the parameter to function. And if we add, if the kernel mark the view as secure, so if it's read-only in the client, the RPC runtime won't actually copy the view to a local buffer. It will directly use the shared memory to perform deserialization and passing parameter to function. And we saw during our testing, we encountered a vulnerability that the kernel does not prevent the client to virtual protect the shared memory to read write again. So basically, you can change the memory write of the shared memory in the client, write to it, and during the RPC call.
Okay, so to give you a little context about where we are now, it's like 2 months, during 2 months, we just looked at binary dump, like trying to find out which field do what in the LPC and RPC. And after that, we found out that we found a new UAC bypass. Why not? We tried to send view to other server, and we found out that we could. And we were at this moment where we look at the code and we see this flag, this strange flag, 40,000, sorry. And we found out the little things that tell us that we might be able to change the content of a view during the RPC call. So we are like, it's really strange, and we want to test if our hypothesis is true. So we tried to create a really, really simple server with only one method, and the method is like the method poet that takes only one parameter named Rololo, which is a string. And all this method do it's like the simple method in the world. It prints the parameter Trololo, so it prints our string. It waits for 1 second and it prints the parameters again. There is no magic, no exploitation, I guess, in this kind of function, sorry. But we will try to see what we can do with the little logical bugs that we found before. So we made a call. We were able to make a call to this method using a secure view, and we will show you in WinDBG what we found out about the call and some aspect of the call. Thanks to Paul yesterday, we are all and you are all expert in WinDBG now. So I will explain these few lines. The first line shows us that we are at the first instruction of the poet method, and at this given time, we're trying to print the content of the Trololo string. So the Trololo string contains my first message, which is the parameters we send to the server at this given time, and that's it. We just wanted to print my first message. But what's interesting is that the address of my first message. You can see that the address is A5000C. Okay, no problem. And if we look at the address, what's under the address A500C in a memory speaking aspect, we can see that it's a page file, a map file. In fact, it's a shared memory. It's our view. Okay? So you send a view with some parameters inside, and you see that the function, which is just a simple function with a string, the content of the string is in the shared view. And as a proof, you can see that at the beginning of this memory page, we have the size of the string, 0, the size of the string again, and the size. And this is the NDR serialization of a string. So actually, the Trololo parameter directly point back to the view. What does it mean? It means nothing like that, but with the logical bug that we found, we know that we are able to change the content of the view at any given time during the call. So we are like maybe able to change the string during the call. Like, it's not something you should be able to do, but whatever, why not? So we try to write a little POC. Yeah, little POC. So I will really try to explain this really quickly. We have the RPC connection and binding, of course. We create a section with the flag 4000. Okay. We map the section in our own process, sorry. We force the call. We pack the NDR, so là, it's really like the serialization of the string, my first message that we saw before, and we craft a message with a view. So we craft a message, we set up the view, we set up the view attribute flag to 4000 again, we set up the view base to the view base we just mapped, and important, at the end, we write in the view our string, our parameters. So the parameter, which is the NDR serialization of my first message. After that, we just send the message. It's an asynchronous send. We send the message and we are back in our process. And we use the vulnerability we found to virtual protect the memory to read-write again. So at this given time, we have a call, a remote procedure call going on, and we are able to change the parameter at any given time. For a simple example, what we've done here is sleep half a second, as the server is sleeping a full second, and we're changing in the memory the string to vulnerable. And you can see that we are jumping over 3D words because the first 3D words at the size, the 0, and the size of the string again. And what does this exploit do when we try it again, the Puet method, is that indeed we are able to change the parameters. As you can see, the first print my first message as expected, but after waiting 1 second, when we print the parameters again, it's a different parameter. So you've like a function that have 2 different parameters at two different times during the function call. And it's like not normal at all. And we've seen that we have like over 100 interfaces that we can hit. So maybe we can find a target, and maybe in one of those targets we're able to trigger a talk to, or maybe a double fetch, or something like that, in some high privileged service from low integrity. So let's find a target.
So we did find a convenient target located in store SVC service. We were interested in the method 14, which is called SVC move file inherit security. Basically, it's move a file and set the name security information of the new file. The interface identifier is BE7F, version 0. So let's dive into the code. The SVC move file inherit security takes 3 parameters: the old file name, the new file name, and the flag for the move file. The first thing that it does, it's impersonating the clients, which means that the server thread will be running with the client privilege. So our privilege, so no privilege. We are running in low integrity, so we don't have any privilege. So this move file will be unprivileged and call with our arguments. And then it's called the RPC revert to self, which means that the server get back its own privilege. And the server, the store as this is server, run with the user anti-authority system, so with the system privilege. Then it's called set name security information with the new file, and in order to set the name security information. And the thing that interests us here is that if the call to set name security information fail, the move file is reverted. So the new file name is moved back to the old file, like by inversing the parameter. And this move file will be executed as system user, so with system privilege. So if we are able to reach this move file and to change the parameter, a new file name and old file name using our shared memory vulnerability, we will be able to move any file to anywhere in the system. So the requirement for the exploit are to reach the vulnerable move file and to... So this means that we need the first move file to succeed and the set name security info to fail. We will modify the ACL of the new file name in order to make the set name security information fail. And we need to win the race. We need to change the parameter in between the two move files because before the first move file we will not be able to perform the move file. So it will fail here, and after it's useless. And we will use a Windows opportunistic lock to lock the file in order to win the race. So here are the steps to perform the exploitation. So you set up 2 useless files and 1 payload file, the file that we want to move anywhere in the system. And you write this file in a writable directory. So we are in low integrity process, so we can only write to app data local low. Then you lock the destination file, so one of the dummy file, using Windows opportunistic lock. You call the RPC service with the 2 useless file and a flag. And so after the move file, during the move file, the destination file will be accessed and the lock will trigger. So in our callback, we will change the function parameter using the shared memory vulnerability and to set our payload and the path where we are to put our payload. And we will remove the white DSC for system user in the ACL of the new source. So here we will change the function parameter. The new file name will be our payload, so we will remove the white DSC right, and the old file name will be the path where we want to put it. So this call will fail because the payload, the system user don't have the right to change the DACL on the new file name, and the move file will happen as system user. So basically we can move our payload to anywhere in the system. With that, we were able to craft a little local privilege escalation exploit. And we'll leave you the challenge of gaining system code execution using only 1 move file. Let's see the demo that pop with the system shell. So here we are in the low integrity command. You can see that here, and this is the last version of Windows without the October patch Tuesday, because it's now patched. So the process is running as low integrity, so we cannot write to the user directory. This is a refuse, access denied. And we run the exploit that exploit the shared memory vulnerability, and magic happen, and the system shall pop. So now we are system, we can do anything that we want, or write anywhere, and do what we want.
Okay, so we were able to gain system privilege from a low integrity process, which is, I guess, pretty cool. But to conclude, what we want to say about this subject and ALPC and RPC, it's like a complex subject. We have maybe 3 months of work about it, and a lot of the work was just looking at dump file and binary dump and trying to guess what is this byte, what is this word, and so. But there is really an interest because few RPC servers expect a custom client. We have been seeing that, for example, in the USC example, where the server does not expect a custom client setting a custom command line, and we were able to have a USC bypass. And we have seen that with the kernel that was maybe expecting someone to try to change the memory, but it was not properly blocking the memory view to be set up again to read-write. And as we've seen really quickly in the fix, it's like an implementation error into the NTOS kernel. There is still a lot of work to be done. We haven't reversed anything. We have done everything. We haven't seen everything. And there is still, I think, a lot of work to be done on this subject, which is interesting. But what we hope is that the open source implementation of the ALPC server client and the RPC client will help others start on this topic. And I really hope that if you want to start on this topic, you might try to find this useful and won't like us take you 2 weeks to send your first ALPC message. True story. And last of all, we would like to thank Microsoft a lot for their quick fix and response, because we sent the report for the vulnerability the same day we sent the CFP to Aclu, so like 3 months and 3 days ago. And they were really efficient, and they made a really quick fix. So thanks to them. And so if you have any question and think we've took a long time, so we will speak about that at the break. But don't hesitate to have a look to Python for Windows, where the code has been pushed just before the presentation. And you can follow us on Twitter as well if you want. Thank you for your attention.
Okay, well, we've got 5 minutes before the break, if anybody's got any questions now. Okay.
Can you elaborate on how you turned a secure file copy into a system access?
Yes, we can. So we use. Oh, sorry. You can see in the demo if you look closely here. We are not moving a file. Actually, we are moving a directory, which is the consent.exe.local, which is for the WinS6S subsystem. And when we will launch, the next time we will launch the consent directory, it will try to find his DLL, the DLL what he requires in order to be launched in the subdirectory consent.exe.locals. So where we have paths or payloads files. And so our DLL will be loaded in consent.exe. So basically we move a directory to consent.exe.local and we have found a way to launch consent. Yeah, it was dirty method actually, but